Let's write the mechanism for this reaction. That will actually get you to the right answer, but that's an unnecessary step. Well, let's review this. This is another of the reactions that we saw last time. Now, one thing we know is obvious is that somebody is going to gain a proton. Why is that obvious? Because we have a strong acid. Almost without exception, in this course, anytime you start with a strong acid, you have to start by having the acid give its proton to somebody. So we have to ask, who should it protonate? Now, your answer is that it would protonate the water over here. And I can see why you would say that, because sometimes it will protonate the water. The problem is that that doesn't help us to get to the interesting product here. After all, we always know that in water there's some hydroniums. I remember even in neutral water there would be 10 to the -7 hydroniums. So it's not really interesting to us to draw the product when this protonates the hydronium. Is there anybody else around for this acid to give its proton to besides the oxygen?
To the alkene.
To the alkene. Let's draw what the mechanism for that would look like. Good. And the other product of this step is sulfate. Let's talk about that step for a second. Why is this a reasonable arrow? Why is it reasonable for this to be at the tail?
Because it wants the hydrogen.
And why? Why is it reasonable for that to be at the tail of an arrow?
Because, trying to think of the term and it's slipping my mind.
Now, the important thing is, if it's at the tail of the arrow, does that mean it's donating electrons or gaining electrons?
Gaining? No, it's donating.
Because the arrow tells us which way the electrons are going. It's the hydrogen that's gaining the electrons, right? So we want to ask, is this something reasonable to have donating electrons? Well, we know that in the past we've seen that things with negative charges, or delta negative charges, like to donate electrons. But last time we also memorized that carbon-carbon pi bonds also like to donate electrons. We also saw.
Is that an electrophile? The alkene?
You're asking if this is acting
Yeah.
like an electrophile? Well, you tell me.
I can't remember.
Does an electrophile gain or receive electrons? So let's think about that term, electrophile. Is an electrophile a positive lever or a negative lever?
Negative.
Because electrons are negative, and phile means lever. So this is a negative lever, or to be less dramatic, a negative liker. So,
So then no. It's a nucleophile, right?
Yeah, it's acting like a nucleophile because something that loves negatives would be something that is too positive. Or something that wants to react with negatives is something that wants to receive electrons. You can even see that from the name. An electrophile is something that wants to receive electrons. It's a lover of electrons. But this is trying to get rid of its electrons. So it's acting nucleophilically. Because our nucleus is positive or negative.
Negative.
Our nucleuses of an atom, positive or negative. Do you know who lives in the nucleus of an atom? Do you know what?
Electrons and, protons and neutrons.
Protons and neutrons, which are positive. That's right. So when people say nucleophile, they really mean proton lover, because in the nucleus is the protons. This is really a term for proton lover or positive lover. Well, a positive lover wants to donate electrons to something positive. It wants to find something positive to donate electrons to, and that's what this pi bond is doing, is trying to donate the electrons. We saw last time that we basically just have to memorize that carbon-carbon pi bonds are nucleophilic. The reason for that is that these pi electrons would be happier if they could become sigma electrons. Sigma electrons are more stable than pi electrons, so they want to get out of the pi bond by being donated to a sigma bond. But we can just memorize that carbon-carbon pi bonds are nucleophiles, but also that means they might be basic, because bases also donate electrons. Oftentimes things that are nucleophilic are also basic, and that's really what this double bond is acting as now. It's kind of acting as a, I guess it's a matter of taste, whether you call it a nucleophile or a base. Either way, it's donating electrons to this hydrogen over here. Maybe it's better to think of it as still acting like a nucleophile and attacking the hydrogen. Okay, so anyway, this is a very reasonable arrow. The key thing is carbon-carbon pi bonds like to be at tails of arrows. Carbon-carbon pi bonds like to be at tails. That doesn't mean that they can always be at the tail of an arrow. There might be restrictions of the reactivity, but in general it's reasonable for them to be acting like nucleophiles or bases. So they're a good thing for an acid to protonate. They're a good thing for an acid to protonate. We didn't form a stereocenter here, so we don't have to worry about forming more than one product here. So to review, the mistake that you made at the beginning is you started by protonating the water. And in a sense, that's not a mistake, because probably some of the waters will be protonated, but that doesn't give us that doesn't help us to get the interesting product here. The way to get the interesting product is to protonate the double bond. And it was good that you remembered the structure of sulfuric acid, that we need to draw the structure of sulfuric acid to really show the mechanism here. Well, let's continue with the mechanism. Now we can use the water at this step. The role of the water here is not to get protonated at the first step, but to act as the nucleophile in this step. And then you showed the water losing a proton. Now, why does the water need to lose a proton here?
It's too positive.
But I think you left that out of your picture. So that's important. Remember that the charges are not an afterthought. In a way, they're the most important part of the picture. This oxygen was at the initial tail. It's losing electrons, so it ends up positive. The only reason why we need to get rid of the proton here is to get rid of this positive charge. So it's very important to put that in. And we might also notice that this regenerates the sulfuric acid, which shows that this was just an acid catalyst. Was this Markovnikov or anti-Markovnikov? Because the electronegative atom, the oxygen, ended up on the more substituted carbon because, again, it was attacking second. So it attacked, we formed the more substituted carbocation. When the water attacked, it did not form a stereocenter, so we didn't have to worry about the stereochemistry.